The last directed graph that we're going to talk about are directed acyclic graphs, or DAGs for short. These are directed graphs that have no directed cycles. So a directed cycle is a cycle in which we can start at one vertex and follow a directed path, only following outgoing edges, and wind back at the same starting vertex. So this is a directed cycle. A DAG, directed acyclic graph, doesn't have any of these, and it's a directed graph. For example, this is an example of this is a DAG. So we have this cycle here, however, this isn't a directed cycle. So B can reach D and C can reach D, but D can't reach B. So this is not a directed cycle. There are a lot of graphs which naturally are or form DAGs. So for example, version control, commit history forms a directed acyclic graph. A family tree without any time travel would form a DAG. And also any task schedule which has a valid prerequisite ordering. Now for digraphs, directed acyclic graphs can be exactly characterized by a topological ordering. So this is a label of vertices, so that we would label every vertex from 1 to n, so that if there's an edge from one vertex to another vertex, then the first vertex comes before the second vertex in a topological ordering. So for example, there's an edge from A to C, which means in a topological order, vertex A would come before vertex C. So I have here a labeling of vertices following one topological order. They're not unique, but they characterize directed acyclic graphs in the sense that a digraph has a topological order if and only if it is a directed acyclic graph. This is useful to find so that we can immediately determine if a digraph is a DAG, if it has a topological order that it is. And this is also useful for finding in some situations such as the task scheduling problem, how we can accomplish tasks in such a way that all prerequisites are satisfied. So why would we want to know if our graph is a DAG? Say we had a digraph represented by tasks that had to be performed. If it wasn't a DAG, then that would mean that there is no sequence in which tasks could be accomplished which successfully satisfies all prerequisites. For example, if there was some kind of cycle prerequisite, like if we had a computer science class that, let's say it was CS 432, and it also had a prerequisite of CS 432. This would be an example of a prerequisite that wouldn't be able to be satisfied. So knowing if we have any of these type of problems, if we have a valid task schedule, is useful. All right, so I have an example here of another graph that has a valid topological order. So that vertex ordering gives, remember, if we have an edge from vertex A to vertex B in our graph, in a task schedule graph, means that task A must be accomplished before task B. That task A is a prerequisite to B. Then in a topological order, vertex A would come before vertex B. So this is an example of a labeling to vertices which satisfies this condition. If there's an edge from one vertex to another vertex, then that vertex occurs earlier in that order. So this topological order also gives an order in which we can perform all tasks which satisfy a prerequisite. So for example, before you study computer science, you must wake up. So this is the first task which occurs. Before you can dream about graphs, you have to fall asleep. So this gives an ordering in which all prerequisites could be satisfied. Again, this isn't unique. We could, for example, study computer science and then nap and then eat, and this would still be a valid topological order. So how would we find this? Well, one way we could show is just to argue about this kind of intuitively before we get to a formal algorithm on how we would accomplish this. If we have a directed acyclic graph, then that means there is a vertex which has no outgoing edges. Well, we're going to label that vertex as being the last one which occurs in our ordering, because since it has no outgoing edges, then it can't be a prerequisite to any other vertex. So we can safely label that one occurring last. And then just decrement a counter, remove it from the graph. By removing this vertex, we maintain that the remaining graph is still directed and it still has no cycles because we only got rid of a vertex, which means that there is still a vertex that has no outgoing edges. So we can safely remove that vertex because it's not a prerequisite to anything else, and label that as occurring next to last in the topological order. So this will give us a valid topological order, but the only question here is why would this actually run in big O of n plus m time? Because here we're showing to remove a vertex and then we have to find another vertex that has no outgoing edges, so it's not immediately clear algorithmically how we could complete this efficiently, but we can use a depth first search in order to do so. So we have here what I've shown in red is the same depth first search that you know and love, and the only difference here is what is shown in blue. So in order to turn this into a way in which we can find a topological order, we can figure out how many vertices there are. This is n. And when we're finished with a topological DFS call on a particular vertex, because we'll repeatedly recursively call this until there is no other vertex which can be reached, then when we're finished with all of these calls, we've gone through all incident edges, all recursive calls to DFS, then that means at this point in time there is no other vertex which can be visited. We're at a vertex which has no outgoing edges. Otherwise we would have followed that outgoing edge. So in this case, we'll label that vertex with label n, and then decrement that counter. So let's see how this looks on an example graph. So this is our directed acyclic graph. We can start that topological DFS from any vertex, because if there's some vertex that hasn't been visited yet, then we'll just start at another vertex. So let's say we start at this top one. How does DFS work? We'll follow these directed edges. Suppose we followed this path first until we reached a vertex where from here there were no other directed edges which hadn't yet been visited. So let's mark these now. I'm not sure if it'll hold in the next slide. I'm drawing it this way. So we've marked this as having been visited. We label it with, since there's 9 vertices, we're going to label this as the 9th vertex, and then work our way back. Now from here, took away my red pen. From here, we have no other edge that we could travel through. There's no other outgoing edge that we haven't yet already visited. We already visited this edge. So we're going to label this as occurring next to last in our order. So this is 8. Now from this vertex, we can follow another path to this vertex. So we're going to label this one as 7 because it has no other new edge to a vertex that we haven't already visited. Now we're going to label this as 7 and kind of work our way back. This will be 6. And this one we can't just label yet because we've got another path that we could follow. So we'll follow this path as far as we can until we reach this is the last new vertex. So any other edge isn't a discovery edge. This is leading back to an old vertex. We're going to label this as vertex 5. This one as 4, 3. This becomes vertex 2, and then our last vertex here is 1. Now if you had started your topological DFS at some other vertex, you may get a slightly different order, but you would still get a valid topological order in the sense that if we have an edge from A to B, then in a topological order, vertex A comes before vertex B.